Here we go. So question number 4. Question 4 says, magnesium phosphate has a KSP of 1 times 10 to the minus 24. What's the molar solubility of magnesium phosphate? A and 0.01 molar sodium phosphate. So let me just write the formula of sodium phosphate for you. Sodium phosphate is Na3PO4. So if I'm only concerned about phosphate, guess what? For every 1 mole of sodium phosphate, there's 1 mole of phosphate. Agreed? So therefore, I'm looking at the common ion of 0.010 molar phosphate. I ignore the sodium. And we're looking at not sodium phosphate, but magnesium phosphate. Sodium phosphate soluble, 1 single arrow, Jordan. Magnesium phosphate's insoluble, 2 arrows. So we say Mg3PO42, solid, in equilibrium with 3 magnesiums. Yes, and 2 phosphates. Okay, it's the phosphate right here that I put 0.01 molar at. This is still 0 because I don't have any magnesium in A. Nothing's mentioned about magnesium here in A. And this is Z. So Z minus X, Z plus, or not Z plus, 0 plus 3X, and 0.010 plus 2X. Notice I don't use the coefficient in the I part, do I? Don't use the coefficient at all in the I part, because this didn't come from magnesium phosphate. This phosphate came from sodium phosphate. So that's why I can't use coefficients at all, ever at the I. Ever at the I. Only in the C and in my powers. So I'm left with Z minus X. I'm left with 3X. And I'm left with 0.01 plus 2X, but that's really just going to be approximately, Kyle, 0.01. And Narik says, hallelujah. Don't want to have to do that extra math. Okay, so KSP is 1 times 10 to the minus 24. And that's going to equal 3x cubed times 0.01 squared. Now, that's going to simplify to this. 27x to the third times 1 times 10 to the minus 2 squared. Now, what's 1 times 10 to the minus 2 squared? 1 times 10 to the minus 4. You multiply those two numbers together, right? 1 times 10 to the minus 4. So now divide both sides by 1 times 10 to the minus 4, so that goes away, that goes away. And over here, 1 times 10 to the minus 4, what is, right here, what is 1 times 10 to the minus 24 divided by 1 times 10 to the minus 4? 1 times 10 to the negative 20. So we have simplified it a little bit to 1 times 10 to the minus 20. That's what this turns out to be. 1 times 10 to the minus 20. And that's going to equal 27x to the third. So I divide both sides by 27. And I don't expect you to do this without a calculator now. And I raise both sides to the 1/3 power so that that goes away. 1/3 times a third is 1. So that equals x. So this number divided by 27 and then raise that whole thing to the 1/3 power comes out to be 7.2 times 10 to the minus 8 for my x. 7.2 times 10 to the minus 8 for my x. There's my molar solubility. We went from 6.2 times 10 to the minus 6 for pure water. This is what it was up in question number 2. That's what it was for pure water. This is what it is for a common ion present. Now, it's not going to always be that number. It's just going to be less than what it was in pure water. Now, what I've just taught you is how do you get solubility in pure water, and how do you get solubility when there's a common ion there? You get to go and practice. All right? Now, one more question. We're jumping all the way down to 7 because I want to show you the real Q question. The real Q question, and the real Q question is number 7, because number 6 is Q, but it's not looking at what I call total volume. So jump down with me to the next one. So I thought I'd go over a couple pages. One more. All right, here we go. This problem is a little different, and I had my 2 beakers out yesterday. Where did my 2 beakers go? My 2 beakers go. I'll go back. All right, 2 beakers. 20 milliliters of a 0.002 molar sodium chloride is mixed with 30 milliliters of a 0.001 molar lead 2 nitrates. Two solutions. Okay, I'm going to mix one with the other. What comes to mind? Molarity comes to mind. What else? A reaction comes to mind. What else? New substance. Possibly less soluble, yes. More liquid. 20, 30, 50. Oh, there you go. Total volume. Total volume. Total volume. Initially, then, we've got total volume. And that's what makes this problem just a little bit different. It says we're going to take 0.02 liters, Mighty Lakes, 0.02 liters times 0.002 molar sodium chloride. Now hold up and don't grab that calculator yet. We're also going to take 0.03 liters of a 0.001 molar lead 2 nitrate. And when we do the Mighty Lakes, without a calculator in just a second, we're going to get moles of the only piece that matters, which is chloride. And we're going to get moles of the only piece that matters, which is lead 2. And we're going to have to take those mole values and put them over total volume. Okay? Now, let's do another quick little mental math piece. 0.02 is 2 times 10 to the minus 2. And 0.002 is 2 times 10 to the minus 3. What's 2 times 2? 4. What's 10 to the negative 2 times 10 to the negative 3? Add those numbers. 10 to the negative 5, Ms. Matney. Negative 2 and negative 3. One's not an exponent on top of the other. They're both just exponents, so they get added together. So I have 4 times 10 to the minus 5 moles of sodium chloride, which is the same as moles of chloride. Because it's that 1-to-1 ratio for sodium chloride to chloride in sodium. Same thing here. I'm going to say 3 times 10 to the minus 2 times 1 times 10 to the minus 3. We're doing Mighty Lakes, and that's why it turns it into moles. What's 3 times 1? 3. What's 10 to the negative 2 and 10 to the negative 3? 10 to the negative 5. Now, both of those numbers are floating around in total volume. Yes. Both those numbers are floating around in total volume. Okay, so if I get those numbers out real quick, I need to show you something with those. 4 times 10 to the minus 5 divided by 0.05 like 8 times 10 to the minus 4. Yep. So 8 times 10 to the minus 4 molar of chloride And 3 times 10 to the minus 5 divided by 0.05 is 6 times 10 to the minus 4 molar of lead. So here's the question, because we haven't really looked at the question yet. Question says, if I mix those two solutions together, and that's why I made you stop, we got to do a little work up front to have initial values. It took a little while to get to my real initial values when the two beakers are poured together. When they're separated, there's no initial. You've got to pour them together and go, stop the clock. And let me see what I have floating around in this beaker first, initially. And that's what we just did. You got to mix them and stop the clock and say, what do I have in this beaker? I have 4 ions in this beaker. I've got sodium ion, chloride ion, lead 2 ion, and nitrate ion. And the sodium and the nitrate are expected. But the lead and the chloride might not be able to spectate because there may be too much of them. Says who? KSP. Because lead to chloride is insoluble. So when I do this, let me show you what's happening. PbCl2 solid in equilibrium with Pb plus 2 and 2Cl minus. What am I starting with? What am I starting with? Am I starting with solid? What am I starting with? Molarity of 2 ions. So initially, I don't have any solid. Oh, Ms. Matney, whoa. I don't have any solid. But I do have, for the lead, 6 times 10 to the minus 4 molar. And for the chloride, 8 times 10 to the minus 4 molar. Now, do you kind of want to do minus 2x minus x plus x? I sort of do. But let's not until we know that it does that for sure. How do I figure out whether it does that for sure? The question up there is, will a precipitate of lead 2 chloride form? Will a precipitate of lead 2 chloride form? Will a precipitate of lead 2 chloride form? Is it at equilibrium? Is it at equilibrium? Is it at equilibrium? Will a precipitate form? How do you know? We don't. So it's a question. Q. It's a Q problem. It's a Q problem. It's a question. It's a Q problem. Will a precipitate form? In chapter 16, that means Q. In chapter 13, is it at equilibrium? That means Q. Then in chapter 16, will a precipitate form? That's the Q. Yes. Say Q is bigger than KSP, which way the arrow points. Right, because you got to do it like this. You got to put K here and Q here. You got to do it alphabetical. So if Q is bigger than KSP, the arrow is doing this. Okay? So it's pointing towards the solid side. So yes, we have precipitates. It points towards the solid side. If Q is bigger, is Q bigger? We don't know yet, so we got to go find it out. We have to say concentration of lead times concentration of chloride squared, right? Isn't that what Q is? The same thing as KSP, but we call it Q. And when I plug it in, I get a value of 3.8 times 10 to the minus 10. So when I plug in 6 times 10 to the minus 4 times 8 times 10 to the minus 4, and I square it, I get 3.8 times 10 to the minus 10. That is definitely smaller than the KSP. Which way is the arrow pointing? towards my ions. What's that mean? It doesn't precipitate.